everyone, this is a chi-square video for k samples instead of one sample. For this video, we are assuming k different populations, or you could think of them as groups, samples, but they're k distinct groups, and you still have j number of responses. And now we're going to introduce the notation p and then lowercase k, j, as equal to the proportion of observations in category J given population lowercase k. So I'm going to do lowercase k, where lowercase k can be any number between 1 up to uppercase k, and lowercase j is any number between 1 up to uppercase j. Get rid of this. Put the correct bracket there. So for this situation, our setup is a little bit different. We're going to say h naught is equal to p lowercase k 1 equals p1 star equals p lowercase k comma 2 is equal to p2 star, all the way dot 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 lowercase k capital J is equal to, this is dot dot dot, so we're doing all groups, pj star. And I just realized I had switched to k's on the opposite side. So these two values should have been a j. Perfect. Okay, and then the alternative hypothesis in this situation would be otherwise. So one of these groups is different. Before I say that, let me actually rewrite this hypothesis. Another way of thinking about this null hypothesis is the distribution this is just an abbreviation for the word distribution of outcomes is the same across groups. So this relationship would hold for all k, lowercase k, which is in between 1 up to uppercase k. So it's that the distribution of outcomes is the same across all groups. It's essentially the null hypothesis in this situation, and the alternative hypothesis is equal to just otherwise. One of these is not equal. Our test statistic, which we are denoting x squared still, is going to be equal to the sum over all groups, or over all categories. This is a lowercase k for all populations that the observed jk minus the expected jk squared over the expected jk, and we have this as equal to chi-square capital K minus 1 times capital J minus 1. So that's the distribution under H null. So we reject H naught if x squared is greater than chi square k minus 1 j minus 1 at level alpha squared. And so the test statistic is virtually the same. Now we're just doing this across all groups. Note that OJK is the observed number of observations in category J, population or group or sample, let's say group K, lowercase k. And EJK is going to be equal to the product of NK, which is the number of observations in group K, times the probability of that particular group. So this would actually be probability J star, which is the expected number of observations. Expected number of observations in category J, group lowercase k. So an example for this situation, suppose you go to 4 universities, let's say 3 universities, and sample and ask sample students asking their major. Same majors as before. Now, J is still equal to 4. K is now equal, it's the number of groups that we have, that would be universities. And now we have in lowercase k for each university. So number sampled at each university. So those are the differences between these two chi-square tests. Another thing I didn't mention at the last video is that the assumptions for this test. One of the really big assumptions for this test is that all observations need to be independent. So no paired data, no dependent data of any kind, and we're talking about between and within observations. So everybody in one university should be independent of each other, and universities should be independent of each other. So independence all around for every single observation to every other observation in both these tests. The other thing that you need to consider is that when you have an expected count that's very small, you can run into some problems. So the other thing you should have is that the expected number of observations should be greater than or equal to 5, or at least really close to 5, for every single category. And that's it.